All right, let's take a look at sections 15.8 and 9, which is going to cover triple integrals in both cylindrical and spherical coordinates. So just a couple of learning objectives this time. Recall how to use both cylindrical and spherical coordinates, and then solve triple integrals in both of those coordinate systems. Starting with cylindrical coordinates. So we've got a point x, y, z in rectangular coordinates. Then we can use a series of equations to transform x and y into r and theta. So we'll be keeping z in cylindrical coordinates and basically just extending polar coordinates into 3 dimensions. And so we'll use the same equations that we did for polar coordinates. R will be d squared of x squared plus y squared. Tangent of theta is going to be y over x, and z is just going to stay z. Cool. So if we wanted to then go back into our rectangular coordinates or substitute in for x and y, we have x equals r cosine theta and y equals r sine theta. So everything looks fairly similar to the polar coordinates we just did a couple sections ago. If we check out figure 2, we can see a point in space being described in terms of those cylindrical coordinates that we just used. And let's expand on that point for a couple of important ideas. And that'll be describing dV, which is that infinitesimal change in the volume at a given point. In terms of, we'll start with rectangular coordinates, and we're going to expand this into cylindrical, and then later on we'll also see it in spherical. But in rectangular coordinates, it's pretty much just what we expect. dV is going to be dx, dy, dz. Since dV should again be that infinitesimal change in the volume, so it should have it should be a 3-dimensional object. And each of dx, dy, and dz all are 1-dimensional. So if we multiply them all up, we get to a dimension of 3. So we're in good shape. So we just look at a rectangle changing in each of the 3 directions. But let's take that same point and now look at what that's going to be in cylindrical coordinates. So here we have that same point, but we're going to use r and theta instead of x and y. I notice that z didn't change, so I've just left dz in our dimension counter up at the top. But we'll look at the projection of our point into the xy plane, which we can see at the bottom of the pink line, right where it meets the red line for r, which is the radius. And we'll look at how first that projection point is going to change. And what we should see here is that if we project it in the xy plane, we have exactly polar coordinates. Now we're just looking at r and theta in the xy plane, so everything should continue moving the way that we know it does from just polar coordinates. R is the distance from the origin out to our point, meaning that dr can just be the extension or just how that radius is changing through space. When we looked at polar coordinates, we saw that just using d theta as an integrating piece isn't going to be helpful to us because d theta has a dimension of 0. If we look down to that unit circle drawn in by the origin, we can see that that's all grayed out because, again, the angle has a dimension value of 0. And if we wanted to bring that d theta into space where we're actually working, we'll want to multiply it by r. So that if we have r d theta, we can now look at how our point is changing relative to the angle that it's being measured by, but also not just how the angle is changing, we want to look at how the point is changing. So here's the leap from polar to cylindrical coordinates. So when we were using polar coordinates, the radius was the distance measured from the origin out to the point, since we were just in a plane. But now that we're in 3 dimensions, that radius r is actually going to be the distance from the z-axis out to our point. So this other line that I've drawn in up at the top that connects the z-axis out to the point in question, that's going to have the same value as, that will also have a value of r. That's what I should say. Which means that if we look at dr and rd theta in the xy plane, that'll be basically the same as looking at dr and rd theta in the xyz space. Oh no, didn't quite grab everything that I wanted there. So let's try that one more time. And we'll just, hey now, we'll just slide that up here. And we'll use dr and rd theta to describe how our point is moving through space. So I should also come over and put down an rd theta in our dimension calculator, or our dimension table, tabulator maybe. And we're going to use these three pieces to describe dv, since if we multiply those three together, we'll get to a dimension value of 3. So in cylindrical coordinates, our dv should be dz times dr times rd theta, which we will most commonly write simply as r times dr dz d theta. R dr dz d theta. We can go in any which order. So let's actually keep it, let's keep the order that we had there. R dz dr d theta, since it doesn't matter. So that just like in polar coordinates, that r that's going to show up when we bring in a factor, when we replace our dv for cylindrical coordinates, there will again be an r that we have to multiply in along with our integrating factors. So if we take this down to triple integrals and cylindrical coordinates, we should see once again that we have this r show up in our dv. And so this is probably about what we expect. If we have a triple integral and we'd like to do that in cylindrical coordinates, then it's just an iterated integral of our three variables. We'll replace x and y with r cosine theta and r sine theta, and dv will be r times dz dr d theta. So let's put that into practice. In our first example, evaluate the iterated integral in terms of, right now we have dz dy dx, but this is going to be set up rather nicely for cylindrical coordinates. We can see that dz, or for our z values, we're just between 0 and y, so we can replace those bounds relatively easily. And if we look at the projection into the xy plane, we get a semicircle. Additionally, the piece that we're trying to integrate, x squared plus y squared, that will substitute nicely into r squared, making for a relatively easy integration in cylindrical coordinates. So all we need to do is just replace some bounds for x and y. And so looking at the equations for y that we have, we're above y equals 0 and below y equals the square root of 1 minus x squared, which is the half circle with a radius of 1, the top half of a circle of radius 1. And x goes between 0 and 1, meaning that r is going to be between 0 and 1, since that circle has a radius of 1, and our theta is going to be between 0 and pi over 2, since 0 would be the x-axis and pi over 2 is the y-axis. So we should be prepared change over that iterated integral into a cylindrical coordinate iterated integral. So our z values will go from 0 to y. Y is r sine theta, so we'll pop that in. We just saw that r goes between 0 and 1, and then theta is between 0 and pi over 2. We can replace our inside function, x squared plus y squared, that's just r squared, but then we'll multiply by dv, which should again be r times dz dr d theta. dz dr d theta. All right, let's see what we get. So integrating z, since we don't have a z yet, we're just going to multiply that in. So it'll be r cubed times z is what we get after our integration. R cubed times z. And if we plug in, what am I saying? If we plug in 0, we get 0. If we plug in r sine theta, we get r cubed times r sine theta. So that'll take care of the dz element. We still have r going from 0 to 1, and theta going from 0 to pi over 2. This is dr and then d theta. So if we do that r component first, we're integrating r to the 4th, which will integrate to r to the 5th over 5. From 0 to 1, that'll be just 1/5. So 1/5 sine theta. And now we're integrating theta from 0 to pi over 2. Here we have d theta. And if we integrate sine theta, we should get negative cosine. And then we'll evaluate negative cosine from 0 to pi over 2. At pi over 2, cosine is 0. At 0, cosine is 1. So that should be just 1 times 1/5. So 1/5 is our answer. So maybe move that over here. Look a little cleaner. All right, let's take a look at the second example in cylindrical coordinates. Finding the volume of a solid that encloses the surfaces listed below. So we're just going to want to integrate dv, which means we'll need some bounds for these equations. Starting with this top one, that's going to be z equals 9 minus 9r squared. The second one should be z equals, well, it looks like r squared squared, which will be r to the 4th minus 1. And we should make some replacement, or we can now set those two pieces equal to each other to figure out what their intersection looks like to give us some bounds for r and theta. So setting those two things equal to each other, what do we get? R to the 4th, let's try that one more time. R to the 4th minus 1 equals 9 minus 9r squared. So we'll have r to the 4th minus 9r squared minus 10 equals 0, which gives us two options, r squared equals 1 or r squared equals negative 10. R squared can't be a negative number, so that one's out, meaning we just have r equals 1 as our intersection. So the intersection of those two pieces is a circle of radius 1. So just like the last example, we will have r going between 0 and 1. And it looks like we're going to do the whole circle. So theta will be between 0 and 2 pi. So we ought to be able to set up our triple integral then, the volume, which is the triple integral over the region E times just dv is equal to an iterated integral with the bounds that we just solved for, where we have, let's change up the order this time, just for funsies. R goes from 0 to 1, theta from 0 to 2 pi, and z goes from the equations that we just found. So we'll need to decide which one is our top function and which is our bottom function. And if we look at those two pieces, z equals 9 minus 9r squared. If we just look at the z-axis and how our function will move out from that point, we're starting up at 9, and then we have an r squared value that's going to open down. So that starts high and then goes down, versus z equals r to the fourth minus 1 is going to start down at a -1, but then open up since that r to the fourth is positive. So starting high and opening down versus starting low but opening up means that 9 minus 9r squared is our top function, and r to the fourth minus 1 is our bottom function. Then we should multiply in our dv, which is r times dz d theta dr. dz followed by d theta followed by dr. Cool, so let's get going. So if we integrate this thing with respect to z, we don't already have anything related to z in the integrand, so nothing to happen there. It'll just go to r times z, and we'll plug in our two pieces, meaning we should have, there's still two integrals left, so I should put two integral signs. We should have 10r plus 9r. Oh, wait, no, that's not quite right. Yeah, 10r minus 9r squared multiplied by r though, so it'll be r cubed, and then minus r to the fourth times r will be r to the fifth. So notice that it should just be the equation that we had earlier with perhaps, aha, there we go. That's what that equation was not making sense. That should have been an r to the fourth plus 9r squared, although the rest of it still solves out the same. Okay, so same equation that we had before, except it's negative and it's multiplied by r. But let's put in our other bounds. We have d theta going from 0 to 2 pi. We have dr going from 0 to 1. And then these are, this function of r and theta is separable into a function of r times a function of theta. That function of theta is going to be just 1 d theta, which makes it nice. So we can separate this thing out into a theta integral multiplied by an r integral. So theta, if we just integrate d theta from 0 to 2 pi, we will get 2 pi. And if we integrate that r thing and plug in 0 and 1, we should get 10r squared over 2, which will be 5r squared, times 1 is 5, minus, integrating r cubed, we'll get 9r to the fourth over 4, plug in 1, and we get 9 over 4. And integrate r to the fifth, we should get, well, r to the 6 over 6, plug in 1, and we get 1 over 6. And that should be the value or the volume of that region. All right, let's change gears and start talking about spherical coordinates. So this time we're going to want to replace all of x, y, and z in terms of a new radius, which we're going to call rho instead of r. The big difference between rho and r is that our radius rho, which is like kind of Greek for r, is going to be measured from the origin out to the point, no matter where we are, as opposed to r, which was always measured from the z-axis out to our point. So that we have the equations, rho squared is equal to x squared plus y squared plus z squared. Cosine of phi, which is our new angle, is going to be equal to z over rho. We could also say that tangent of phi is equal to z over x squared plus y squared. So let's just pop that one back in. Tangent, we want opposite over adjacent, so that's actually x squared plus y squared over z. I think I said it backwards a moment ago. Yep. Oops, square root of x squared plus y squared over z. There we go. That's our tangent value if we wanted to use it. We could also say that cosine of phi is equal to z over the square root of x squared plus y squared plus z squared. And finally, tangent of theta is equal to y over x. So theta is going to be the exact same angle that we were using from both polar coordinates and spherical coordinates, where it just measures the angle in the xy plane from the x-axis to the projection of our point. Right, so the other equations that I've written below that box are all equations that can let us change from cylindrical to spherical, which can sometimes be a bit more advantageous because the notation cleans up a little bit. So that now we can write that the tangent of phi is equal to r over z. We don't have to worry about as many square roots. So sometimes the notation can just be a little bit nicer if we first change from rectangular to cylindrical coordinates and then cylindrical into spherical. Sometimes that helps, but it's a totally unnecessary step. But it is a shortcut that I will most likely be taking advantage of in the next couple examples. So if that is our polar coordinate or our spherical coordinate system, let's go evaluate what dv should look like. So we are going to keep the exact same theta that we had from cylindrical coordinates. So I've just put those pieces back into our dimension counter. So d theta still has a dimension of 0, so it's not going to be great by itself in dv, since we've got to get to a dimension of 3. But r d theta is still going to be that same piece that we'll want to use to describe how our point changes through space. So we can see that I've got it written out down in the projection in the xy plane, but it'll be the same infinitesimal change if you look up where our point is. Since we described it earlier, we said that it could be done by, earlier in the last example, we said that it could be in any plane, not just in the xy plane. So r d theta won't change between cylindrical and spherical coordinates. So let's look at the pieces that do change. We don't have dz anymore, or dr, because r isn't part of spherical coordinates. So we'll need d rho is the most straightforward. Rho is just the distance from the origin to our point. So if we're looking at how our point is changing relative to rho, it'll just be the continuation of that line. And d rho, just like dr, has a dimension of 1, just in the direction of rho. Nice. So d phi is the new one that we'll look at. And phi is the angle measured between the z-axis and wherever that rho line is. And again, just like theta, d phi has a dimension of 0 because that phi is existing again on some hypothetical unit circle that exists in the, I guess the ZR plane would be the easiest thing to call that. So if it doesn't add anything to our dimension counter, and we still need to get up to 3 dimensions for dv, we'll need something else. So we're looking to get d phi out to where our point actually is in space. So we'll multiply d phi by rho, just like we multiplied d theta by r. So here we have rho d phi is that blue line, which takes it out into space. Notice that we don't want to use rho d theta to talk about how our angle theta is going to change out through space, since that would move us beyond the point that we're interested in. We just want to move out from the z-axis to the point in order to see how that angle theta is changing. So let's go ahead and put rho d phi up on our dimension counter, and we'll say that that thing has a dimension of 1. So if we look at dv in spherical coordinates, it can be d rho times r d theta times rho d phi. And then that gets us out into 3 dimensions. But we have a bit of a problem if we leave things here, although I think that this is a helpful step to look at, because this particular representation of dv calls on a coordinate that we're not actually using. We're trying to express everything in terms of rho, theta, and phi, which are blue, purple, and green, but we also mixed a little bit of red in there, just sort of based on my color scheme, and red isn't part of the spherical coordinate system. So we're going to need to express r in terms of the spherical coordinates that we have available. So if we went back up to the equations that let us change between cylindrical and spherical, we had one that said tangent of phi is equal to r over z. Is that the one we want? Well, it might be helpful later, but it's actually not the one I want right here. Instead, I wanted the one that said that sine phi is equal to r over rho. R over rho. If we look at the triangle that is in the ZR plane, we're looking at this triangle right here. And we should be able to see that if we examine our angle phi, which is down by the origin, this thing has it is a right triangle, since the intersection of r and z would make a right angle. Kind of hard to see in a 3-dimensional shape, but I think we know that the intersection of r and z should be at a right angle. And the hypotenuse of that triangle is going to be rho, while the opposite side is r. The adjacent side would be z. But we're looking at opposite and hypotenuse here, so sine of theta is equal to r over rho. So we could then solve that thing for r and say that it's equal to rho sine phi. And we will use that replacement in dv. So it's going to be a little bit bigger, so I'll expand it a bit. We're looking at d rho. Then we have rho sine phi d theta. And then we have rho d phi. So when we're looking at dv, we will usually just simplify this thing down to rho squared sine phi times the rest. D rho d theta d phi. But in order to remember that extra integrating factor that comes in, which is now a little more complicated than r, since now it's rho squared sine phi, I think it's helpful to remember where each of those pieces are coming from. So we have one factor of rho that comes from d phi needing to be multiplied out into space rather than just on the unit circle. And we have a factor of r that comes from d theta. needing to be multiplied into space. It's the same r that we have in polar coordinates and in cylindrical coordinates. But we need to change r into spherical coordinates, and that's going to be rho sine phi. So that's where the sine phi and the extra factor of rho are coming from. So if we take this thing down now, actually let's mark one more thing up here before we move on. This green arrow should be rho sine phi d theta. Just kind of put our whole collection together. Okay, so if we take this down then to our triple integral theorem for spherical coordinates, we should see that we have that same integrating factor that pops up, rho squared sine phi, just like we found. And a couple of things to note about spherical coordinates and some of the things that we'll use here. Rho, I think, was in purple. We like rho to be positive if we're going to be using this particular theorem. We can work with negative values of rho, but for just this particular theorem, rho should just be a positive number. Theta, we have already looked at theta a bunch. It's got to be between 0 and 2 pi. And then phi is our new one. It's going to bounce between 0, which would be straight up the z-axis, but we only need to do half of a circle with phi. So it's only going to go from 0 to pi. Pi would be going straight down the z-axis. So since theta needed to cover x and y, we need to go completely around the circle in order to get all directions. But since we've already gone completely around the circle in the x and y plane, we only need to do half circle to get the z-axis involved. So straight up for an angle of 0, and straight down for an angle of phi. So let's apply that to a spherical example. So we're going to find the volume of a solid bounded below by a cone and above by a hemisphere. So if we just rearrange that top equation for a moment, we'll call this thing z equals, instead of the square root of x squared plus y squared over 3, the square root of x squared plus y squared is just r. So we'll call that z equals r over square root 3. That thing can be rewritten to give us e square root of 3 equals r over z. And that was another one of the definitions that we were using that lets us change between cylindrical and spherical, and I think the notation just looks a little cleaner. But this should be tangent of phi. Since we know tangent phi is r over z, we also have the equation, it's just x squared, the square root of x squared plus y squared, all that over z. But like I said, this notation looks just a little bit cleaner. We can then solve tangent phi equals square root of 3. And if you remember your trigonometry, or I guess more accurately, your unit circle, if tangent of phi is equal to the square root of 3, that means that phi is equal to pi over 3, or 60 degrees, if you wanted to use the degree system. So that cone is at an angle of pi over 3. That expresses the whole cone. We also have a hemisphere, z equals the square root of 1 minus x squared minus y squared, which if we just rearrange that thing, it should give us rho equals 1. So square both sides, add the x and the y over, we get x squared plus y squared plus z squared equals 1. So rho squared equals 1. And since we just want the top half, it'll be rho equals 1. But I mean, really rho equals 1 would be the full circle. The fact that we're looking at the top half is just going to limit what we use for phi. So if we wanted the volume of this thing, then we need the triple integral over whatever our region is of dv. And let's change that over into an iterated integral. So theta, we're going to go all the way around the circle, so we can just go 0 to 2 pi. For phi, since we're looking at the top half, we're going to start up at 0, which would be starting at the top of the circle, and move down until we get to an angle of pi over 3, since that's where our cone is located. And then finally for rho, we just need to go between 0 and 1, since we're looking at a circle of radius 1. Then multiply in our dv, which means we'll want to remember that rho squared sine phi, that has to show up, because it's part of our factor dv, and then just put the rest of the values in order. Looks like we did rho as the innermost, phi as the middle one, and theta as the outer one. So we'll keep those in order, and then just start doing some integration. If we integrate our rho piece, we're integrating rho squared, which go to rho cubed over 3 from 0 to 1. That means we've got a factor of 1/3. Sine phi is still there. D phi is next. We're going from 0 to pi over 3. And d theta is last, going from 0 to 2 pi. So if we integrate sine of phi, we should get negative cosine of phi. And if we plug in pi over 3, we'll get 1/2. And if we plug in 0, we'll get 1. So we're going to have negative 1/2 minus negative 1. So negative 1/2 plus 1 is 1/2 times 1/3 is 1/6. So 1 over 6 times d theta, and theta integrates from 0 to 2 pi. And there's our function doesn't depend on theta, it's just a constant. So if we integrate d theta from 0 to 2 pi, we will just get 2 pi, and 1/6 times 2 pi is pi over 3. And that's spherical coordinates.